Good day everyone, my name is Raymond. I'm a PhD research scholar in biochemical pharmacology. Today we'll be looking at isotopy and radioactivity. So, now let's look at the nature of an atom. A positively charged nucleus is surrounded by a cloud of negatively charged electrons, which is usually called electron cloud, to form an atom. The number of the orbital electrons is equal to the number of protons in the nucleus. This is known as the atomic number, which is denoted as Z. The mass number of the nucleus is the sum of the proton and neutron. That will give us the mass number for an atom. Let's go to the definition of isotopy. Isotopes are nuclides that have the same atomic number but differ in their mass. So you can see two elements, or let's say the same elements, having the same atomic number but a different mass number. Let's also define radioactivity before we go into details of isotopy and radioactivity. Radioactivity is defined as a spontaneous decay of the nucleus and the transfer of one element to another, resulting in the emission of rays. These rays can be beta particle, alpha particle, or gamma radiation. Now we also have type of decays that we encounter in radioactivity. We have the negation emission, the positron emission, the particle emission, the alpha particle emission, the gamma rays emission, the X-ray emission. Decay by negation emission, when the neutron is converted to a proton by the ejection of negatively charged beta particle, is called negatron, which is B by beta minus is emitted. So let's also go into negatron emission is very important to biochemists. We are going to talk about that in this our lecture. We have the H3, which is the tritium, which is an isotope of hydrogen, and we have the carbon-14 are beta emitters and can be used to label any organic compound. So we can label glucose, we can label fatty acid, we can label nucleic acids. Now the sulfur 35 is used to label methionine. Methionine, which is actually an amino acid that is found in protein. And they use this actually to study protein synthesis. We have the P32, which is a powerful tool in molecular biology and used as a nucleic acid label. If you notice, the nitrogenous base that are found in DNA contains the nitrogen base, which can be a purine or a pyrimidine base, the sugar, which can be a ribose or deoxyribose, and the phosphates, which is actually what is used for connection for synthesis of the nucleic acid. So we have the beta emission. We have the beta emission, which emits isotopes. The big emitting isotopes are most suitable for auto-radiography, particularly for cell and tissue studies. So we have decay of alpha particle emission. Isotopes of elements with high atomic number frequently decay by emitting alpha particle. An alpha particle is a helium nucleus that contains two protons and two neutrons. As you can see, it's denoted as helium 42 plus. An alpha particle have high ionization power, less penetrance, and extremely toxic. So it is not usually used for biological studies. So let's progress. So let's look at the detection and measurement of radioactivity. Various methods have been developed to measure the emission of these particles. We have the auto-radiography, we have the gas ionization detectors, and we have the fluorescent scintillation. These are the basics to detect and measure radioactive in clinical laboratory. What we do in biochemistry is to detect let's say if you're interested in studying the metabolic pathway, you can actually label the enzymes or the ligand of that pathway to measure the flow of those molecules throughout that pathway. So in auto-radiography, a photographic emulsion is used in auto-radiography to see the molecules labeled with the radioactive elements. So for example, we can label glucose with carbon-14, and we can use autography to monitor the movement of glucose within the system. The emulsion is made up of several silver halides crystals, which can be silver chloride or silver bromide. The halide there represent halogens embedded in a solid phase such as gelatin. So let's look at these techniques to measure the length of DNA molecules by auto-radiography. You can see here the cells are incubated with radioactive thymidine, which is actually found in DNAs but not RNAs. So if we're interested in studying the DNA, we'll use thymidine. Or if you're interested in studying the RNA, we'll have to use uracil, because uracil is not present in thymidine. Uracil is not present in DNA, sorry. So you can see here that the cell is incubated with a thymidine that is radio-labeled with tritium, which is an isotope of hydrogen. So after the incubation, the cell is actually lysed and fixed content. Embedded in the content, the embedded content on the slide. The slide is now immersed in a radioactive sensitive emulsion that contains the silver halide. Now in the first case, the incubation of the cell with radioactive thymidine, tritium thymidine, is to make sure that the DNA present in those cells incorporates that radio-labeled thymidine into their own DNA. That's the reason for the incubation. So after some time, we would have assumed that the cell must have taken up that particular thymidine to synthesize new DNA. Now, after the immersion in the radioactive sensitive emulsion, you can see that the soluble ions are washed away. Okay, look at the first one. You can see at this point, the slides, sorry. So you can see that at this point, the slide is dipped in silver bromide, which is the emulsion. You can see it here. You can see it here. It's dipped in silver bromide. So which is further. So you can see here at this point, the radiation activates the nearby the ions to form the silver. So the silver atom here is just like when the silver actually accepts an electron, it is deposited as silver metal, which is dark in color or which is black in color. Well, we use the word dark. So after the activated silver ion is actually reduced to silver metal, the soluble ions are washed away to leave the metal. You can see it is now having a dark spot. It is now having a dark spot at this point. It's having a dark spot at this point. So, which is exposed to light of photographic film. You can see the DNA molecule or the chromosome. You can see the DNA molecule or the chromosome. Then develop to transfer into an image that you can actually visualize using the auto-radiograph. So the summary of the picture you just see of the previous slide is the cells are grown in a solution containing radioactive thymidine, which is the tritiated thymidine, which is the 3H thymidine, that is radio-labeled with tritium. Now the tritiated thymidine is incorporated into the chromosomal DNA of the cell. So the the thymidine is actually used because the thymidine is not present in RNA as I earlier discussed. The chromosomes are isolated by gently lysing the cell and fixing the chromosomes to a photographic surface. 4. The surface is then a mass in a radioactively sensitive emulsion containing silver bromide. You can use a silver chloride, which you can use any silver halide. Now the radiation released from the treated thymidine converts the silver ions in the silver bromide into insoluble metal grains. Following a period of exposure, excess silver bromide is washed away, leaving the silver grains to appear as small black dots. So in 7, when the photographic film is developed, the image is transferred to the film and can be visualized using the auto-radiograph. So these techniques of auto-radiograph have become more important in molecular biology. The weak beta-emitting isotopes like the hydrogen, the carbon-14, and the sulfur-35 are mostly suitable for auto-radiography, particularly for cells and tissue localization experiments. Low energy of negatrons and short ionization track of isotope will result in discrete image that can be visualized. So, in summary, the auto-radiography employs the techniques of radio-labeled. So those elements or those molecules that are radio-labeled can now be visualized using the auto-radiography. So let's also look at the half-life of these radioisotopes, because if we're looking at using an element for auto-radiography, we have to look at the half-life also of that particular radioisotopes, because we know that this radio-labeled molecule will continuously to decay, and when they continuously to decay, they can get to a point where you can no longer visualize them. So half-life of radioisotope is the time period required for the radionuclide to decay to 1/2 the amount of that is originally present. So we have the T-half, which is actually a symbol for half-life, is equal to 0.693 over the decay constant. So every radioisotope have their own decay constant. So if we know the half-life, we can actually predict the decay constant of that particular radioisotope. So the decay constant is constant of a given isotope decaying in unit time. So every radioisotope have their own characteristics decay constants. So let's look at the application of auto-radiography. So auto-radiography provides qualitative as well as quantitative information regarding a specimen. The auto-radiography is used to determine receptor distribution and localization. For example, if you want to know the amount of receptor that is in a particular cell surface, we can actually use auto-radiography to determine it. Now, if you remember previously, we were told that elderly people are prone to COVID-19 virus because of their distribution of the angiotensin converting enzyme receptor. And because of that receptor, the quantity of the receptor they are likely to have the COVID-19. While the younger generation of the children are not susceptible compared to the older generation because of the expression of that particular number of receptor. So radio might actually also be used to determine the receptor distribution and predict the age grade that is susceptible to the virus. So we can also use auto-radiography in the application of electrophoretic transfer of proteins from polyacrylamide gel to nitrocellulose sheet during blotting. So that's what we use in Western blotting, to transfer the protein to a film so that it can actually be visualized. We also use this to study cytogenesis of the forebrain, application of radiopharmaceutical research, and application in radioimmunoassay or radioimmunoelectrophoresis to study protein, the amount of protein that is found in the cell and the relative abundance